Hey guys, welcome back to my series on restoring classic late 40s American black and white electrostatic televisions. In this series I'm going to be pointing out some of the differences between these sets and the more common magnetically deflected sets, give you some tips, some tricks, some suggestions, some pitfalls to avoid to get these up and running. Well, for better or worse, we're taking a deep dive into this guy. This is the high voltage oscillator coil. We've got 3 coils of wire on this, essentially. We've got this heavy wire here, the yellow wire, just a couple turns around it. This goes to the filament of the 1B3 high voltage rectifier. Yeah, the filament for the high voltage rectifier gets its power from this. It only runs on something like 1 1/4 volts versus all the rest of the tubes run on 6.3. So they get its power from this. It also means if the oscillator isn't running, that tube doesn't get any filament supply. Alright, well, right underneath that is a pancake coil. That is the primary, and then we've got these 2 pancakes. Those are the secondaries. They stack one on top of the other. Why exactly, I don't know, but I presume it's to get enough high voltage. I've seen some that have 3, 4, 5 of these all stacked up and wired together. Now, hopefully you will never have to go anywhere near this, or think about it, or get involved with it in any way, but I do get to that in a moment. Now, we also have this capacitor on here, which is in parallel, I believe, with the primary. And this forms, we also have this wire coming out here going to this hoop that wraps around the high voltage rectifier. This forms an oscillator, tank oscillator. It sort of feeds back on itself. This cap, the inductance of these, plus this tickler feedback is what keeps it running and sets the frequency. I'll show you the schematic in a moment here. It's pretty simple. We have a 6V6 and Motorola. They use a 25L6. I've seen other sets use a 6Y6. Basically a beam power tube going to the coil. So the coil's in here. So there's the primary, and there's that domino cap. It's a mica cap. In this particular set, it is 1300 picofarads. And there's a little 5.6K resistor here to provide a little current limiting biasing there. And then here is our secondary. Many turns of wire. And there's that little loop there going to the high voltage rectifier. And we've got a choke down here in a 0.05. That's to keep noise from this getting back into the set. And then there's a 180K resistor here going to that feedback. That's like a grid leak bias. And that's it. The power for it comes right off the tube, so the highest voltage point in this set. So you want to feed as much voltage you can into this to get the most voltage out of it. And ideally, this is set to run at the most efficient frequency to give you the highest voltage with the least amount of losses and least amount of waste power, which would be heat. So why am I talking about it? I'm talking about it because the coil that was in this set, everything was working great. We were getting a good 6 kV out of it. It failed. How did I know that? Well, I noticed the picture wasn't as bright as it used to be. Let me clear some of this stuff out of the way. And I went and measured the high voltage, and it was down to 2 kilovolts. Tinkered around, hoping it was something like the 6V6 tube or some other component. But no, so I investigated further and found that this top pancake here was open. Right about where my finger is. So I found the break, and I found the general area where the break was. So I had continuity from the bottom up through this, and I had continuity from this into this. I scraped away for the insulation in a few points and isolated it pretty well there. You put a blob of solder on there to restore continuity, wired it all back up. Now I'm down to 1.3 kilovolts. So what's going on? How did I get 2 kilovolts before? Internal short or internal arcing. When I disconnected power, measured it, it was open, but with power going into it, it was producing high voltage, but much diminished. So why didn't my repair work? These things are sensitive, just like with an audio transformer or a flyback in a magnetically deflected set or a power transformer. If you have a short somewhere in the secondary, yeah, you'll still get voltage out, but the transformer is going to start getting warm, and you're not going to get as much power out as it would normally. Why? Because you got eddy currents going in there, you've bypassed some turns, electrons aren't flowing the way they're supposed to. Especially with this kind of thing where it's a resonant circuit, you want to have a certain Q factor and efficiency, and by shorting some turns, that's how those ring testers work. Like on this piece of equipment right here has a ring test built in. That's like a tuning fork. The way ring testers work is you apply a short pulse to a coil, and if there are no shorts in it, no opens, it'll resonate at its natural resonant frequency, and you'll get decaying sine waves. Just like striking a tuning fork. It decays away. But if there's a short in it, it'd be like damping. It'd be like taking a tuning fork and squeezing it with your fingers or something like that, or wrapping a rubber band around it. You're dampening it. So there's really no hope in repairing this. Could you rewind it? Sure, if you had a very, very nice coil winder. There are many, many turns. It's 1 kilo ohm of resistance between these two. It's 500 ohms in each. There are many, many, many turns, and it's not just wrapped around. It's like a basket weave pattern. So, okay, that's got to go. I have a number of spare parts chassis. So I pulled this guy out of one of them. Now, unfortunately, it's broken. So at least we get a chance to talk about a few problems you might encounter. So these are ceramic shafts that are internally threaded. A screw at the bottom, screw at the top. It's not uncommon to see the top broken out. Why? Because somebody put the screw in there and they cranked down on it, or put the wrong screw in with a different thread pitch and bust out the ceramic. Be careful. Also, these 2 pancakes here, they're wired together, and then they go down to here. There's an incredibly thin wire going down from the second pancake to this lug down here. You just look at it the wrong way, it's going to snap. So if you ever have to take one of these out, handle it in any way, do anything to it, be extremely careful. Can you get a replacement? Theoretically, back in the 40s, you probably could order one from Admiral or Motorola. I don't think I've ever seen one for sale at a swap meet or on eBay or anywhere. And I took a quick look at the SAMs for this chassis, and they didn't list anything like from Merit or Thord Arson for a replacement. I've heard the Motorola coils will work okay in this. They basically look the same, but it's a different value capacitor. So I'm not entirely sure. Now let's get to something else. So this is from an Admiral set, but it's got this springy thing on it, and these wires are yellow. Here's the original. It's got orange wires, and this is a steel clip. It's not a spring. So that led me down to do a little bit of research as to, like, are these the same part or aren't they? Because remember, this came from a 19A1 chassis. This came from a 17T1, which is the later and last edition of this chassis. And remember, we were getting like a good, healthy 6 kilovolts out of this. But this died. Now, why did it die? I presume it arced between some windings or something. So I've only ever worked on one other of these. It's one in my collection I got, I don't know, 5, 6, 7 years ago. I'm not sure if I did a video on it. It has a chunk bust out of the cabinet. It was a little chewed up. But I went back and looked at my reference photos from when I worked on that. And I don't remember too clearly, but in the photos, I see myself, I replaced this coil in that one too. And it also had this steel clip. Now, I went around my collection, my garage, my storage locker, and pulled out 4 19A11 chassis. And they all have this type in them with the spring. So it got me thinking, since this was the last edition towards the end of the whole electrostatic TV fad phase, did they use a different coil, and did they push it harder to get a brighter image out of it? And the coil is slightly different, and they put out a full 6 kV, and I got me thinking too, well, 6 kilovolts, that's the maximum voltage you're supposed to put on this picture tube, and all the caps are rated for a max voltage of 6. So we're right at the limit of everything. Now, more conventionally, when I've worked on these types of sets, you get more like 5, 5.2, 5.5. You don't get a full 6 out of it. So maybe that coil was being run too hot, and that's why it burned out. I don't know. We'll never know. The point is, this has got to get replaced. Now, let me give you some pointers on how to, if God forbid you ever have to replace one of these, is how do you get them out safely, easily. The filament leads, those are tough to get at. They're up under here. If you're going to be taking this board out to work on these pots, replace the 4.7K resistors in here, it's way easier to get at those 2 wires. But even with this in place, you move these wires aside, you can get in there. Now the other 3 wires, when I first did it, I removed them down below and fished them through a hole and all that. No, that's dumb. I quickly realized, no, don't do that. Do it from the top side. If you're taking one out that's bad, just clip them. Just clip the leads right here. I'm going to do that right now. No, actually, when I put this in, I didn't solder them very well because I anticipated I'd be taking this back out. But generally, just clip them up. Clip the 3 wires off up here. There's enough length on them that you can strip a little bit back, and when you put the new one in, and you just feed it in. There are 3 eyelets here, 3 lugs. Clear them out with solder, or clear the solder out with desoldering braid or a solder sucker. And then you just need to strip a little bit of wire off and just feed it into the eyelets. I wouldn't go crazy with trying to wrap the wire around it. Just get it in there and put a little bit of solder on there and solder them in. Because some of these fine wires go to these same lugs, you don't want to overheat them. You don't want to accidentally burn through those wires. You don't want to get snag on them. And then there's that mica cap, which has really heavy leads wrapped around. And then there are very fine leads going to those same lugs. So if you want to mess with this cap, do it very carefully. And I suggest you do it while you've got it out, not while it's mounted down in the chassis. It's very hard to get at when it's down in there. So let's get this guy out. And this, if you're lucky, because I've already done this a bunch of times, it's loosened up. If it's stuck on there pretty good, get a little thin screwdriver up in there and carefully pry it off. Once you get it up a little bit, it's easier to get a tool in there. As I've noticed that these caps, they vary from tube to tube a little bit in diameter. This is the original tube that was in here. This one is pretty tight. You don't want to yank on this because you're going to rip it right out of that. So be careful. Did I mention be careful enough? And then this you can slide up. There's enough slack. You can get it off with the tube in place. And then get this out of the socket. And then you got more room to work on this. Alright, this is heated up. Sorry, I've already done this a few times, so these wires I should just be able to heat up and pull out. And remember, this coil's bad, so I'm not too worried about damaging it. I suppose if I was really invested in this set, I could send this out to somebody with a coil winding machine, and they could examine this and figure out how many turns there are. If you know the wire gauge and you know the resistance, you can get some idea of how long the wire is. There's no way you're going to unwrap it and count the number of turns, because there are hundreds or thousands of turns. Alright, so those 3 wires undone. Go down below, and there's one screw holding it in. This is the trickiest part. Top one's not too bad. The bottom one is pot's really in the way. There's one, the other one. Basically have to come in. From this way. You just can't get in from the side of the top. There's just not enough. At least not with my iron. I just can't get in there. Alright, there's the other one. Those are heavy gauge wires and they go through kind of a small hole, so be careful and straighten them out before you feed it through, and voila, there it is. I'll hang on to it. Who knows? Well, we're on the topic. Here's a look at a couple other coils. I believe this is from a Motorola set. Somebody coated it with red insulating varnish. You notice there's a slightly different value cap. This is 1250. That's what Motorola used. And hey, the ceramic shaft is broken on this one too. I don't know if they did this as a preventative measure or do they really have arcing and they needed to do it. I've never had any issue with arcing in these before. And then this, I really don't know what this came from, but I mentioned earlier that sometimes they have a whole bunch of stacks. Well, here you go. This does kind of look familiar. Just can't remember what kind of set, but on this design, they don't have that tickler coil. So there's the primary. And here's your secondary, and that tickler coil is actually this winding up here. They don't use that clip that goes to the rectifier. Notice there's no lead coming out with a spring or clip that would go around the high voltage rectifier. This is this cap. Then here's those 3 wires like we had with the other one. And then there's this wire which would go to the feedback for the oscillator. And a cap and resistor up here, I'm not quite sure why. But yeah, it's more than one way to do it, but same basic idea. Now, supposing your coil was missing or it was damaged beyond repair and it was a rare set and you really wanted to get it running, there are other options. This I think would be the easiest. It's a DC to DC converter power supply. 12 volts in, 6,000 volts out at 1 milliamp. It would be perfect for this application, but it's $136. However, I am curious to try something like this because it's going to produce, assuming this works like it is advertised, really clean, really solid, nice high voltage. It's not going to droop when the scene gets bright like the original design does. Now, where would you get 12 volts DC? Well, we've got 6.3 volts AC powering the tubes. Put a full bridge rectifier on that, maybe 12 volt, like 7812 regulator on it. Power it off of that. There's a little trimmer on this if you want to tweak the output a little bit. Dimension wise, it's in millimeters. I can't quite do the math in my head. I think that would fit, or you find somewhere into the chassis to try it. Alright, we're going to do a little bit of experimenting. I hope this proves educational and gives us some useful results. So I'm going to take the fixed 1300 picofarad cap off of this coil and replace it with one that's around 1000 or 1100 and put it in parallel with this variable cap. I was going to use one of these little guys, but then I realized the range on them is only about 1.5 picofarad to 10 picofarad. We need much more than that. So I went through a kit that I picked up at the early television convention swap meet last year, I think. They had a bunch of little modules that you could build your own circuits, including this antenna tuning coil. And if I go one extreme, we get about 32 picofarads, and the other I get about 430. So figure we can go about plus minus 200. So if I use something that's like 1100 or 1200, we can go plus minus the 1300 that is in there now, the fixed And I happen to have this bag of mica caps, vintagey ones, so I'll look around in here. We got all sorts of values. I see a 900 right away. So you want to look for one that's around 11 or 1200. There's 3000, 2000. So let's see what I can come up with. And then we'll get it all assembled. Now, it's not ideal to have this and the leads and all that. It should all be compact, but I don't think it'll make that much of a difference. The free running frequency, according to the Motorola service info, is about 140 kilohertz. That's the only mention I could find of that in any service info. I looked through a variety of chassis, and they have very minimal information about this circuit. They just say it's a self-resonating kind of tank step-up transformer, and that's about it. Then I'll show you the waveforms, the frequencies. They give you the voltages on the 6V6, and that's about it. Alright, I have everything rigged up. Here's my little 3-inch CRT glowing down there. I have my high voltage probe and variable cap up there on the chassis. So let's put this on the output of the high voltage rectifier. And at 3.75 kilovolts with the cap fully open. The cap range is around 1000 to 1400. Let's adjust it. So I'm increasing the capacitance now, and the high voltage is going up. And up, and up. So this is about what I was getting before with that fixed 1300 in there. Around about 4.3, 4.4, keep going, 4 point. And now it's going down. And now it's fully in the maximum capacitance position, so we can back off. So my thinking is I peak this, then I can measure the value of it and then install a fixed capacitor as close as I can get to that. But honestly, that's about where it was with the 1.3 in there. Now there is another adjustment with that coil around the high voltage rectifier. You can move it around, but I haven't seen that have a huge effect. Yeah, if you go all the way like to the base of the tube, you could even stop oscillating. But when you're kind of in the middle, but I'll move it here. I'm sliding it down the tube now. Yeah, it's going down. Let's go the other way. And if I keep going, it starts going down. So, yeah, I mean, it's disappointing, but not too surprising that if you put the original cap in there and put the feedback coil about where it was when I started, that's like peak efficiency. So what else can I do? Swap tubes. I'm going to try to dig up a new old stock 6V6. I've tried half a dozen used ones, and I got about the same results with all of them, so I don't have high hopes for that. High voltage rectifier. There are different styles, and I found in the Motorola service info they talk explicitly about where to position that feedback for different types of high voltage rectifiers. So for example, this is the early style, and this is the later style. On the older style, they say to position it kind of at the bottom of the bell, just above that gap. That's the plate, and that's the cathode down in there. And on the newer style, they had it up a little bit higher, but not a huge difference. But we can play around with these, and which I already have and didn't notice a huge difference, but I'm willing to do it again. The final thing we can do is tinker with the resistor values. The 5.6, I went higher and lower. It made a bit of difference, but not huge. I don't think I've tried changing the 100 or the 180 though, so we can try those. Again, it'd be easier to have a variable. So those substitution boxes I showed a while back are like things like this for science kits where you've got like a pot in a box with 3 leads coming out. You can clip into things. This is where they're handy when you are designing a circuit or troubleshooting, and because unsoldering and soldering in a new resistor value, like say that for 100 I try a 56 and 82 120, it gets tedious real fast, so I'll do what I can. So if I left everything right now at 4.3 4.4 kilovolts, it would work fine. It would work absolutely fine. It might even prolong, or it would prolong, the life of the CRT. So if it comes down to that, I'm okay with leaving it. Also want to show you, if I turn that brightness down, we're at about 4.3. If I turn it up and up and up, it starts dropping. So maximum brightness and down to 3.8. But that's normal because you're loading it down. That's why I was curious if I got a solid state high voltage supply that didn't drift with a heavier load, how much better would the set perform? And by the way, magnetically deflected sets do the same thing. Unless you got a really fancy high-end Dumont or something that has a regulated high voltage output, they all droop with increased screen brightness. Tried a few different high voltage rectifiers, no significant difference. Now let's try this. It is a new old stock 6V6 GTG, accepted March in 1945, so military graded. Let's see what this can do. Yep. Alright. Let's pop that guy in. And the final thing I'll do is tinker with those resistor values a bit. There we go. I should mention too, the high voltage output does vary with line voltage. I'll tweak my variac and I'll show you that in a moment. Alright, so we're back up. Our CRT is glowing. High voltage. We're getting a little better. Alright, that tube did help. Got it up to 451. Tweak that trimmer cap. Interesting. With a different tube in there, adjusting the trimmer cap got it up even higher. Like it changed the resonant frequency with a different tube. The tubes do have internal capacitance. I wonder if this is a little different. Alright, we're heading in the right direction. Just going to go through the whole range on that cap. I've also heard it'll make a difference, or can make a difference, when you put the cover back on the box, because that's going to affect stray capacitance as well. Alright, 463. Alright, now I'm going to tweak the line voltage a little bit. Right now I'm right about 117, so I'm going to drop it down to say 112. Notice the high voltage is dropping. I'm down to about 110. I'll go the other way, go up to about 125. Now we're up near 5 kilovolts, which is getting close to my target. Now our outlets here, if I was to plug this right into the wall, it's typically around 123 or so. So if I was just to plug this right to the wall, it'd be closer to 5 kilovolts. Also, something you guys can't see because it's a little hard to position, but I want you to see the face of the CRT as I'm adjusting this high voltage and see the effect it has. It's not just brightness. The screen actually changes deflection a bit. There, let me position things for you. Alright, so you watch that. Now I'm adjusting the trimmer cap. So this is where we have lower high voltage. And now it's going up, and then it drops down. So you think that you can see when it drops down, two things happen. It gets dimmer, but it also gets bigger, because it doesn't take as much energy to deflect the electrons, so the raster increases in size. So you really want to get all this stuff balanced as best you can. Now you might be wondering what's actually happening when I'm adjusting the variable capacitor. What we're doing is we're trying to tune the primary to the self-resonant frequency of the secondary. So this variable cap is right across the primary coil. I've got it fully meshed now, so maximum capacitance, and here's a waveform on the screen. Frequency is about 104 kilohertz, and volts peak to peak is about 9. So I'm going to start adjusting it. Oh, let's see, our high voltage is 3.9. So let's start adjusting it for less capacitance. Our high voltage is going up, but this amplitude is dropping. The frequency is going up a little bit, so we're 105.5. So you might think it's odd that, hey, the primary voltage is going down, but the secondary voltage is going up. Yeah, that's the idea. We want to get to where it's most efficient, where they're closest in resonance, and the peak output voltage should be when this is at the lowest amplitude. So what effect would modifying these resistor values be? Well, the 180K, that's a grid leak bias going to the gimmick feedback. If we increase that, it should put more negative bias on this and less current will flow through this, so it should decrease the output voltage, I would think. So we can try lowering that, but I think that's going to have a minimal effect because this is somewhat self-adjusting. It's kind of the nature of a grid leak. And then there's 5.6K, which is the one I tinkered with earlier, and it had some effect, but honestly I can't remember if increasing it or lowering it boosted the output voltage. That's going to the screen. That's where I had my scope clip on there. But let's try it. I'll throw in a 4.7 and I'll see what I got. Maybe a 6.2, 6 or 6.8. We'll go 4.7 and 6.8 and see what effect that has. Even better, let's go with the potentiometer. So I put a 1K resistor in series with a 10K pot, so I can go anywhere from 1K to 11K. Let's adjust it for the best output voltage, measure it, and we'll put a fixed resistor in with that value. I've got it adjusted about halfway right now. Alrighty, let's see where we are at. 4.27 kilovolts. Let's increase the resistance. It's dropping. 4.15, 4.1, 4.0, and at 11K we've got about 3.97. Alright, let's go the other way. Three, 4.4, 4.5, 4.6, 4.7, 4.8, 4.9, 5. Alright, so if I go all the way down to 1K, we get 5 kilovolts out. I'm good with that. I'm good with that. 390 ohm resistor. Now I turn the pat back up a little bit. Let's repeat the experiment. About 3.8. Let's decrease the resistance. 2, 4, 3, 5. And going all the way down doesn't really get me anymore. Still around 5, so let's try going with 1K. So I'm going to remove everything, clean up all my work, go with 1K resistor and a 1200 picofarad cap. Let's button this up.